Okay, we are here and we're going to turn a whole new page today and try to keep it in the time limits. I'm sorry, guys, I ran over last time. I usually try to make sure that we keep our presentations within the allotted time. We're going to talk about Introduction to Fuzzy Inference. Now, this is a very interesting story. It turns out that in 1965, there was a professor from UC Berkeley named Latvizada, and he wrote a paper called Fuzzy Sets, I believe it was. And that was a singular paper that started a whole technical movement. And he called them fuzzy. There was kind of a backlash. People didn't like the idea of fuzzy because it was kind of it meant it wasn't precise. It wasn't mathematical. It wasn't very good. And but nevertheless, it came on. Every year, there are 2 or 3 international conferences on fuzzy systems. IEEE has a transaction called the IEEE Transactions on Fuzzy Systems. And so certainly it has been applied and really has had an impact on technology. Now, it turned out that when Zada published his paper, Z-A-D-E-H, he published it in 1965. It was one of the few cases where an entire field was launched by a single person using a single paper. Another example of that was Claude Shannon, 1948. He published this great book called A Mathematical Theory of Communications for Bell Labs, and he established the whole area of what is now known as Shannon information theory. And like Zada, there are transactions, there are international conferences which are dedicated to the work that Shannon does. When I teach the graduate course in Introduction to Information Theory, the first part of the course, not literally, it basically goes through Shannon's original paper. He wrote it so wonderfully, so icely that it was great. It's the same thing here for this fuzzy inference and for this fuzzy logic. There was initially a big pushback in fuzzy logic because fuzzy logic was used to control systems, and they most particularly in the area of washing machines and dryers and different things. And the reason was it was so obvious to use it. We communicate in what I would refer to as fuzzy linguistic variables. You can be in a car and I can tell you to back up the car to, just this far from a wall. And you will be looking at me in the mirror and I say, come back, more. Okay, slow down, slower, stop. Nowhere in there did I give a numerical result. Yet somehow by using these fuzzy words like fast, slow down, slow, these are what are referred to as fuzzy linguistic variables. And we communicate with them all the time. We say, for example, I saw a man, the man was tall. What does tall mean? Is there any quantitative value associated with the tall man? No, tall is a fuzzy linguistic variable. You might have a different interpretation of exactly what tall is. I might have a different interpretation of what tall is, but nevertheless, it's something that we can still talk about it, right? So the question is there a way to take common English language that uses these fuzzy linguistic variables and reduce them to machine code, to reduce them to a mathematics? And that's what Zada did in 1965. He reduced this to a specific language. The primary application of this was in the area of control theory. And at the time, there was a great inertia in so-called classical control. And the IEEE has the Control Systems Society, IEEE Control Systems Society, and they publish these journals. And some of them, like the transactions on automatic control, became so full of papers that nobody understood. They were so esoteric. They were so out there mathematically using Ito calculus and all of this strange stuff. They were very rarely reduced to practice, but there was an incredible movement towards this analytic approach to control theory. So when fuzzy logic came along, there was a pushback. You remember the hype curve that we talked about? The hype curve goes up and then it goes down. And the hype curve was really difficult for fuzzy logic. For years, it lived in disrespect until finally the Japanese came along, and the Japanese took Zada's fuzzy logic and reduced it to practice and began to come out with fuzzy this, fuzzy that. I remember visiting a colleague of mine at Nagoya University, and I had heard that fuzzy was a common word there, that a lot of the Japanese knew what fuzzy was. This was in, I guess the mid 90s or something like that. And so I asked the daughter who was practicing her English with me, I said, do you know what fuzzy is? And she goes, oh, fuzzy. No, I don't know. And I thought for a minute, and then I realized that the Japanese wouldn't pronounce it that way. So because I had heard her father, Toshio Fukuda, say fudgy. And so I said, have you ever heard of fudgy logic? And she said, oh, fudgy, yes. And she knew exactly what it was. It was used in commercial, it was used in promotion, and it caught the attention of the world. And people like General Electric and other people started to take note of fuzzy logic. Now, and began to reduce it to practice. Now, let's take a look at the application of fuzzy logic. Could you, for example, use fuzzy linguistic variables to dictate how long a washing machine should work? How long a wash cycle should be? Well, if the clothes are dirty and the load is heavy, then you want to wash it for a long time, right? If, on the other hand, the water is not dirty, the word is turbid. If the water is not turbid and the load is light, then you want to wash for a short time. That's just obvious English interpretation of how a washing machine should work. So can you take these sort of sentences, reduce them to a mathematics to control the way that fuzzy logic is applied, and apply it to, for example, a washing machine or a clothes dryer or a number of different things? Well, unfortunately, the people who were in this classical control way of doing things did not like fuzzy logic. And in fact, they published their disdain about fuzzy logic. You had no poles in the left half plane. You had no root locus plots. Those of you that have had control theory have known about this, right? Have you heard about that? Not if you've heard about it, okay? There was none of that. It was just it was taking these reductions of fuzzy linguistic variables and reducing them to practice. And that was what the fuzzy logic was about. And that was pretty incredible. And the thing is that it worked. So one of the pushbacks came from an Australian guy who was really into classical control theory. His name was Bob Bitmead, and he wrote in IEEE Control Systems magazine, this was a while back, he said the image which is portrayed is that of the ability to perform magically well by the incorporation of new age technologies of fuzzy logic, neural networks. You can see there's a pushback in neural networks too. And that's another very interesting historical historical story is about the pushback of neural networks and the fight between the people that were doing connectionists versus the rule-based systems. So we have these new age technologies of fuzzy logic, neural networks, approximate reasoning, and self-organization in the face of dismal failure of traditional methods. This is pure, unsupported claptrap. Wow, that's a pretty strong term. He didn't like it, which is pretentious and idolatrous in the extreme and has no place in the scientific literature. Unfortunately, Bitmead was a victim of academia, and he forgot what engineers should do. Engineers take theory and they reduce those theories to practice. And if you can reduce a theory to practice, there's no arguing. It works, right? If you can reduce it to practice and market it and it sells better and it does a lot better than previous technology, there's no arguing with success. And so that was what Bitmead did. Now, The guy that came up with the fuzzy control was not Latvizada, but a guy named Mamdani. And Madami read this and he wrote back. I thought this was very, very telling. He wrote back that fuzzy theory's delayed exploitation outside of Japan teaches several lessons. One is the traditional intellectualism in engineering research in general, and the cult, I italicize this, I like this, the cult of analyticity within control system engineering research in particular. So Mamdani, who created this fuzzy control, was pushing back and against this resistance of a paradigm shift, and said, look, it works. Don't argue with me. And George Bernard Shaw, this is an appropriate quote. All progress means war with society. So if you do have something which is new, you're trying to get it in, it's very difficult to get it in. So what is fuzzy logic? What was all this controversy about? This controversy was about, first of all, the idea of fuzzy sets. And we're going to deal with the idea of fuzzy sets. We are used to crisp sets. We are used to things being within a set or not in a set, right? The set of people over 6 foot tall, they're either in the set or out of the set. Now, if you use a fuzzy linguistic variable, some things are more in the set than they are out of the set. Conventional or crisp sets are binary. An element either belongs to the set or it doesn't. Fuzzy sets, on the other hand, have grades of membership. Now, this is the way I think you can consistently think about this. We can talk about a fuzzy linguistic variable, and we can vote on it, and we can talk about this fuzzy linguistic variable on a scale of 1 to 10. Right? How far is something on a scale of 1 to 10? How far is it from, how far is a city from Los Angeles? Well, if we look down here, let me get my little pin here. Where'd my pin go? There it is. Okay, it's not working. That means I got to reach up here. I got to follow the cord. And for some reason, when I pull it out and push it back in again, it works. Okay. So we're talking about the set of cities far. Well, that doesn't work very good, does it? Okay. You can see my cursor, right? Oh, you can't see my cursor? Okay, you're just going to have to follow along with my I guess that the marker doesn't work on this new, this new set where I'm in the lower right corner is a new Zoom feature, and apparently they don't have the ability to write on the PowerPoint, which you do in the normal sharing. So I think we can get through it without too much problem. So let's talk about the idea of the set of cities far from Los Angeles. Now, far is a fuzzy linguistic variable, right? It's something which you would interpret as different than I would. So think of cities which are far from Los Angeles on a scale of 1 to 10. Clearly, at the bottom here, we see that this, by the way, is referred to as a membership function. It's how much the element is in the set. It's not either in the set or out of the set. It's a little bit in the set, a little bit out of the set. And we're trying to decide how much that is. So as far as cities far from Los Angeles, the city of Los Angeles clearly is 0, 0. It is not far from Los Angeles. So therefore, we would assign it a membership value of 0. Chicago, we might put a 0.5, New York a 0.8, and London a 0.9. One of the things which is interesting about fuzzy sets, if I were to put these down, the 0, 0.5, 0.8, and 0.9, and I were to ask you to come up with your estimates, they would be different, wouldn't they? Probably. They would be different. And that's something which is recognized in fuzzy sets. One of the interesting things is we can all be assured, if your assignment and my assignment, that each one is monotonic, that each one of these numbers is going to get bigger and bigger as we get further away, right? So at least we have this monotonicity going for us. Like you might, instead of 0, 0.5, 0.8, 0.9, you might have 0, 0.4, 0.6, and 0.8 or something like that. So both cases, the numbers are going up as the cities are going. So at least that there's that commonality. Even that sometimes isn't assured. Now, with this discrepancy, you might think, well, that kind of screws things up for fuzzy logic because of these different interpretations. Interestingly, as we'll see, it doesn't, and fuzzy logic works very, very well in many sorts of applications. The term FAR used to define the set is a fuzzy linguistic variable. And you can sit down and you can talk about fuzzy linguistic variables forever. They would include close, how close is something, how heavy something is, how light, something is big, something is small, smart, fast, slow, hot, cold, tall, and short. In fact, some of these are not ordinal, not measurable. Do you notice that when you go to the doctor, sometimes the doctor might ask you, tell me on a scale of 1 to 10, how is your pain? Has anybody ever been asked that by the doctor? What is your scale? What is your discomfort on a scale of 1 to 10? Well, what he's asking you for is a fuzzy linguistic variable describing the pain. Interestingly, there is no way to measure pain in terms of numbers. There's no instrument that you can put on a person to measure the pain from the inflammation and things like that. That's not necessarily true for something which is hot or cold. We can measure the temperature there. Tall and short, we can measure the height. And so some of these fuzzy linguistic variables do have a measure associated with them. Other ones, such as pain or beauty, if you have a beauty contest, you might say, this person is more beautiful than that person, okay? That'd be a fuzzy linguistic variable, which cannot be measured by a number. I think you see this in the Olympics, which we just had. You had high diving. I don't know if they had high diving. I didn't watch the Olympics, but if they had high diving or ice skating or something like that, you have judges on the side that figure out what the fuzzy linguistic variable is in the area of perfection of the performance. And they hold them up. And notice, just like I mentioned, everybody might have a different value. Some might hold up a 10, some a 9, some an 8. Each one of them saw the same performance, but their assessment of the fuzzy membership function on those is the fuzzy membership function is going to be different. And that's okay. That's something we live with. That's something that we do know. Now, this one, by the way, I made a link to these slides if you want to get a copy of them on the Google Sheets. This first one is wrong. Fuzzy membership functions are typically between 0 and 1. You can be totally not in the set, which is a fuzzy membership function of 0. You can be totally in the set, which is a fuzzy membership with 1. What's wrong with this as a fuzzy membership function? It goes to infinity when x is equal to 2, right? I should have had something like a +1 here on the denominator, and that would have made it okay. Or I could dink with it, but just ignore that because this is wrong. I also gave you a paper write-up that goes over this material in a tutorial, like a journal tutorial sort of form. But you can make up your own fuzzy membership functions. For example, we're talking here about the set B of numbers near to 2 or close to 2. Near and close are fuzzy linguistic variables, right? And we can talk about this membership function of numbers which are close to 2 as being, for example, this double-sided exponential here, this Laplacian, if you will, that peaks at 2, probably with a value of 1. Because if a number is equal to 2, it's very near 2. It's totally in the set, right? So it should peak here at 1. And then it goes down the further away you get from the value of 2. So we can assign functions in terms of membership functions. And these functions many times can be, arbitrary. I fit I fit a Laplace here. Maybe you could do a Gaussian curve, an e to the minus x squared curve, and that would also be a possible membership function for the set of numbers near to 2. So you can see that there are lots of ways where you can choose these membership functions close to 2. You know, we're familiar with sets and subsets. There are such a thing as a fuzzy subset. A fuzzy set A is said to be a subset of B if its membership function for A is always less than or equal to the membership function for B. We could, for example, take the linguistic variable far and then talk about another linguistic variable called very far. Very far is kind of a subset of far, isn't it? Right? So let's call the membership function for very far equal to the membership function of far squared. Now, the membership function for far always lies between 0 and 1. So if you square it, you always get a smaller number. You always get a smaller number. So therefore, the membership function, if you were to look at it graphically, the membership function for the subset would always lie below the original function. One of the things that we want to do when we generalize the fuzzy membership functions is we want to make sure that conventional crisp logic, crisp sets applied. What are crisp sets? Crisp sets are the sets that you remember, know, and love and have studied. Something is either in the set or outside of the set. Okay? So something is in the set or outside of the set. That should be a specific case of the crisp membership function. I'm sorry, a special case of the fuzzy membership function is the crisp membership function. So everything that you learned in logic about sets and subsets so far, you should be able to apply it to crisp sets, and it should apply also. Let's look at an example of a crisp membership function. The numbers greater than 10. The numbers of greater than 10, you're either in the set or you're external to the set. So a membership function for this crisp set is 0 up to 10. And then if you're greater than 10, you're totally within the set. So all membership functions for crisp linguistic variables are always binary. They're always 1 or 0. They're either in the set or not in the set. And anything we do in fuzzy logic, we should look at the crisp set equivalent of what is happening, and it should reduce to all of the logic that we are familiar with. When you first hear about fuzzy, there's this tendency to think, well, isn't that just probability? No, in fact, there's a number of ways to measure uncertainty or variableness, if you will, in a quantity. Fuzzy is not equal to probability. Let me give you an example here. Very, very sobering pictures. Billy has 10 toes. The probability Billy has 9 toes is 0. Do you agree with that? Nod. Okay. The fuzzy membership of Billy in the set of people with 9 toes, however, is non-zero. So that's one example. The probability of Billy having 9 toes is 0, but the fuzzy membership of Billy in the set of people with 9 toes, however, is non-zero. Because the fuzzy membership for people with 9 toes would peak at 9, and then it would probably go down, maybe like that Laplacian sort of exponential decay, and it would not go to 0 at 10 toes. It would be something else. That's one example. Let me give you another example. Okay, you're coming up and you have a bottle and you are just dying of thirst, and it's a bottle of liquid. And one of the bottles is a liquid, and it has a probability of 1/2 of being rat poison and 1/2 of being pure water. You got that? That's bottle number 1. There's a 50-50 chance it's beautiful water that will quench your thirst. There's another, but it's just as equally likely that it contains rat poison and it will kill you. Okay. The second bottle's contents in the fuzzy set of liquids contains lots of rat poison, and the fuzzy membership function of that, a liquid containing lots of rat poison, is 1/2. So in one case, in the first case, we have a probability of 1/2 of being rat poison, 1/2 of it being pure water. The second bottle's contents in the fuzzy set of liquids containing lots of rat poison is 1/2. So both of these have a number assigning 1/2 to them. My question to you is, which bottle would you choose to drink out of? Anybody want to hazard a guess?
Number 1.
Number 1, right? Because if you absolutely need to drink something, you would rather go for 100% pure water, which you have a 50-50 chance, as opposed to something with a membership function of 1/2 in the set of all liquids containing lots of rat poison. So hopefully these will help differentiate between probability and fuzzy membership functions. They're both between 0 and 1. But fuzzy membership functions are typically heuristic. It's just something we assign to them. We have a basic understanding of what they are. So the meaning, as you can see here on the bottom, the meaning of 1/2 for the two bottles clearly differs significantly and will impact your choice should you be dying of thirst. I thought this was a very, very clarifying example of the differentiation of the two. And I would cite a friend of mine, Jim Bezdek, who is a fuzzy guru, who came up with this example. Now, here's something that's going to blow your mind. Are you ready? Probability can be crisp or it can be fuzzy. You have crisp probabilities, and you have fuzzy probabilities. Let me give you an example of a crisp probability. You flip a coin. The probability that you would come up with a heads is 1/2. And if I ask 1,000 people, what's the probability that I would flip a coin and it would come up with 1/2? Everybody would agree that the probability is 1/2. Do you agree? Yet on the other hand, you hear sometimes on the news, the weatherman saying the chance of rain tomorrow is 50%. So you switch to another channel, and on that other channel, you say the probability of rain tomorrow is 60%. Can you see these probabilities are not the same? They're a heuristic interpretation of probabilities. So interestingly, probabilities can be both crisp and fuzzy. Again, a crisp probability would be, for example, the probability of rolling a die and getting 3 pips on it. Pips, by the way, are the little dots on the die. So that would be 1/6, right? No question, it'd be a crisp probability. Where if you talk about things such as weather forecasting and such, you're going to have different heuristic probabilities, which are themselves fuzzy. So interestingly, you do have a combination of fuzzy logic and crisp logic applied to probability. Now, once you have a set, we've talked about subsets. Normally, you think of a subset as, a set kind of in a Venn diagram. You have a set, and then you have a corresponding subset, which is totally subsumed within the larger set, right? That's what a subset is. What about these different operations of and, or, and complement? What happens with fuzzy sets? Well, if we apply them, first of all, we must meet the crisp boundary conditions. So whatever rules that we come up with for and, or complement are not, not elements not in the set, then if we apply a crisp evaluation to it, it better work. It better fall down to the sort of logic that we're used to. And another thing for these, as far as and or, what else must it be? It must be commutative, right? So if you have the intersection of sets A and B, that should be the same as the intersections of B and A, right? Same thing for the union. The union of A and B is the same as the union of B and A. It probably should be associative. It should be idempotent. We'll talk about idempotence later on. And it probably should be monotonic. Now, these last three are maybe a little bit, if you excuse the pun, a little bit fuzzy, but we will elaborate on them. We will elaborate on them when we get to the idea. So let's look at some example fuzzy sets to aggregate, to combine either with an or to take the complement of them. We're going to have two fuzzy membership functions. On the left, on the bottom left, you can see this is the fuzzy membership function of numbers close to integers. This is the fuzzy membership function for numbers which are close to integers. Is that okay? So they peak out right where there's an integer and then they come down. And so if you're halfway between an integer, well, you're really outside of the set. You're out of luck. But if you're right on an integer, it has right on an integer, then it has a value of 1. Again, this is somewhat arbitrary. This is something that I just chose. What the heck? And then we're going to revisit the set B and the numbers which are close to 2. And you can see on the bottom right here, as the arrow goes into my head, that this is something that we saw before. This is the double-sided exponential of numbers which are close to 2. Now, here are some things that we would like to do. We would like to, first of all, do a fuzzy union or a logical OR. The logical OR, in other words, the membership function of the fuzzy set A, and we use this just like in regular logic. This is the union symbol of plus. The fuzzy membership of A and B of X is equal to the maximum of the two membership functions. Now, it does turn out that we need to well, I'm sorry, it turns out that this was the example of the fuzzy union, which was given by Zada in his original 1965 paper. This is what he suggested. And it turned out there was a lot of wisdom in choosing this intersection. Taking the maximum between the two membership functions. But this is not to say that there are other ways that we could perform the maximum other ways that we could perform the union operation and come up with a combination. So you can see there's a lot of arbitrariness of fuzzy logic. Not only there's arbitrariness in the fuzzy membership functions, there's the arbitrariness of the logical operations. But as to not confuse things right now, let's just stick with the maximum. We would like it to meet the crisp boundary conditions. We'd like it to be commutative. Is it commutative? Looking at the equation, sure, because it doesn't matter which area that you put here. It is associative. It's idempotent and monotonic. And we'll get to this. Let's see, do I give an example here? Yeah, let me stop sharing the screen here for a second. And okay. And share my whiteboard. One of the things which we decided here was that the membership function for A or B of X is equal to the maximum of mu A of X and mu B of X, right? That's what we decided. Now, One of the questions we asked, does this meet the CRISP boundary conditions? Say, for example, on a line, we have the numbers which are less than 20. Whoops, that wasn't very straight, was it? So this is the membership function of all values less than or equal to 20. So this is a value of 20. Is that okay? Notice it's binary. It's either a 0 or a 1, isn't it? Right? Then we can have the set of all membership functions which are greater than 10. Is that okay? So this is a crisp example. So what is the fuzzy membership function? It is the maximum of these two membership functions. Can you see that the maximum of those two membership functions is going to be what?
Always 1.
It's always 1, isn't it? Let's take another example, which is a little bit more instructive. I hadn't planned it to come out that way, but that's the way it went. Here's 10 and 20. And we're going to do, again, a membership function for all values greater than 10. And now we're going to have another membership function of everything which is less than 0. Whoop, what was that? Didn't come out too well. Okay, those are the two membership functions. Now, if we do a union here, what do we obtain? We obtain the membership function here. Correct? That's the maximum. Now, here's my question to you. Is this the union that we would expect for the crisp sets if we did the union? Exactly. It is the same exact result that we would expect for the crisp sets. So therefore, this union operation of the maximum meets the boundary conditions of the crisp set, which it needs to do. Correct? What about the associative value? The associative value says that mu of A, whoops, I don't know why I put a circle around it. That's the associative value. Does this fit the associative value? Absolutely. Sure it does. Sure it does. Absolutely no problem. I can't find my PowerPoint now. Okay, well, my PowerPoint went away. Let me see if I can open it up here. There it is. Okay. There we go. So what else do we have to do here? What else do we have to do in terms of making sure that this is a good operation? It is commutative, it's associative, it's idempotent. Idempotent means if you do it twice, it's still the same thing. So it's like sweeping a floor. If you sweep a floor twice and you do a good job the first time, the second time leaves exactly the same results. That's idempotent. So is A union B the same as A union B union B? Yeah, it is. It's exactly the same. So therefore, nothing happens with it. And it's monotonic. It's monotonic in the sense that the bigger the membership function, then the bigger the intersection. So if we have two membership functions, the bigger the membership functions, the bigger the bigger the union is going to be. Now we've done this for the intersection. What do you think happens when we do the? No, we haven't done the intersection. We just did the what? The shoot. I'm doing multitasking. I can't do that here.
Union.
Yeah, we just did the union. What do you think happens when we do the intersection?
Probably the minimum.
Yep, exactly. Well, I'm learning about this new application on Zoom. Yeah, if you have A and B, then you have the minimum. So what we wanted to do before we did that is we wanted to take these two sets that we had. Remember the set of numbers close to 1? And then we had, or I'm sorry, the set of numbers close to integers, right? That was that little triangular wave, right? That was a membership function for the repeated triangles. And then we had numbers which were close to 2, which is given by that exponential. If we look at the union of these two fuzzy sets, X is near an integer or X is close to 2, we get the maximum of the two, which is given by the relationship shown at the bottom here. So it's just taking those two curves and at every point choosing the maximum between the two. So this is the fuzzy membership function of the union between the two fuzzy sets. Kind of cool. And as we said, the intersection, the logic and, is given by the minimum. Again, this was what was chosen by Zada in his classic 1965 paper. And it turned out to be very, very nice. It has a lot of great properties. However, there are other ways to do to do intersection sort of operations. This is one of them. We'll stick to this for now. First of all, do you think it meets the crisp boundary conditions? I will let you look at that and convince yourself that indeed it does meet the crisp boundary conditions. Think of two crisp sets of just 0 and 1, and we want to look at the intersection. What's the intersection? The intersection is when both membership functions are 1. The intersection is where both membership functions are 1. Both membership functions are totally within the set, and that corresponds to the maximum. If we have one outside of the set or both outside of the set, then no, it doesn't belong in the intersection. So it does meet the crisp boundary conditions. It's clearly commutative in the sense that if you replace the mu A and mu sub B, if you flip them around, it still works. Minimum is commutative. It's associative. If you do A dot paren B dot C, it's the same as A dot B paren A dot B dot C. Okay, it's exactly the same thing. It's idempotent and it is monotonic. Monotonic in the sense the larger the set is, the greater the membership function is, the bigger the intersection is going to be. Of course, both of them have to be sufficiently large in order to make the minimum. So we have minimum as the logic and what do we get here? If we were to look at our previous two fuzzy membership functions, where we looked at x, which x is near an integer, and x is close to 2, we would take the minimum of these two membership functions, which is shown on the right here. So you have to have both the conditions that the number is close to 2, and you have to have the membership being close to an integer. Let's talk about the complement. If you think of a complement of a fuzzy set in a Venn diagram, you have a little circle, which is a set in the Venn diagram, and the set is all the points inside the circle. The complement is all the points external to the circle, right? So the question is, what does this correspond to in terms of the fuzzy complement? Well, it turns out that we can simply take 1 minus the membership function, and we get the complement of the set. This does meet the boundary conditions of a regular complement, which is nice. And if we were to look at the set A, complement of the set A was all the numbers close to an integer. The complement of A would be the set of points which are not near an integer, not near an integer. By the way, you have to be careful here, because there's sometimes you might think of, let's talk about the set of tall men. Well, the complement you might think is the set of short men. No, you can't do that. You have to be very, very careful in that, because you run into bumps. You think of the set of tall men, and you think of the set of men that are not tall. You have to put that not in front of the fuzzy linguistic variable in order to talk about the corresponding fuzzy set. So here is an example shown at the bottom of the complement of x when x is not near an integer. Now we have min and max. What about some of these operations? We know, for example, in regular logic, a dot b plus c is the same as a plus b dot a plus c, right? If you're doing Boolean logic, that's the way it works out. Well, guess what? That works out for the min and max too. It isn't obvious, but it works out for the min and the max. Because the first set here is the minimum of a comma the max of b and c. The second one is the minimum of the max of a and b and the max of a and c. And if you run through the logic of what's happening here, you find out, my goodness, that does work. So intersection is distributed over union, and it turns out the union is also distributed over the intersection. So these are properties which we see in regular crisp logic, which are applicable here. And here is the one that I just mentioned. Min-max fuzzy logic has a union distribution over intersection. So the union distributes over the intersection just like it does in normal crisp Boolean logic. It works exactly the same. So you see, we've taken Boolean logic here, and by using this min and max, we have generalized it to a case where the membership functions are not binary, they're not crisp. And the question is, how do we use this? But the interesting thing is that, yeah, we have something that meets these so-called crisp boundary conditions. And this is true for the min-max fuzzy logic. Now, here's something which is interesting. Min-max fuzzy logic obeys De Morgan's law. You remember De Morgan's law from just elementary logic? That the complement of B intersects C is the same thing as the complement of B plus the complement of C. That's De Morgan's law. Guess what? Using the 1 minus for the complement, using the max for the union, using the min for the intersection, this works out too. So De Morgan's law is applicable.
Dr. Marks,
yeah.
Sorry, is that A supposed to be a C?
Is that A supposed to be a C? Yeah, let's see, yeah, it is down here in the bottom. Yes, thank you,
Okay,
Sam.
thanks.
Yeah. Yeah, what Sam was saying on the bottom equation, we have B and C, and then I stick an A in there in the right part of the equation, and that A should be a C. Thank you for pointing that out. Is this obvious to you, that bottom equation? Corrected? It isn't obvious to me first on seeing it. I think it's something you have to look at and give a little bit of head scratching. And let me ask you, how would you prove this? If I were to ask you to prove this in a mathematical sense, how would you prove it?
So one way you could do it is simply just use substitute the formulas for mins, maxes, and 1 minuses.
Okay, what's a formula for min?
So that'd just be the mathematical min. So, I mean,
Yeah,
you'd have to use sort of the logic induced by that that operation itself.
Okay, so how would you do that? I mean, that's easy to say, Colin. How would you do it?
Well, I mean, you need to know the properties of mins and maxes. So build up theorems that say, min distributes over maxes. If you're really rigorous, you could prove it has a mathematical ring structure.
Let me give you another proof, and let me ask you if this is a proof. What about if I just chose a B is equal to 0.7 and a C is equal to 0.5 and saw if it worked, and then switched it around? The first one is the B is greater than C, and then I do B is less than C. Would that suffice for a proof, just using those two numbers in an example?
Be an engineering proof.
It'd be an engineering proof. That's right. And we have to be careful. You've heard, for example, the engineering proof that all odd numbers are prime, right? 3 is prime, 5 is prime, 7 is prime, 9, well, that's an exception. 11 is prime, 13 is prime. Therefore, all integers are prime. So that's the engineering proof that all odd numbers are that way. But I think that you could just say if B is greater than C and show that it worked, and then you do B is less than C and show that it worked. I don't even think you have to do that because of the symmetry of the equations. You just have to assume that B is greater than C, right? And if you assume that B is greater than C and showed that this worked, then that would suffice as a proof. I think a general proof. Okay. That's one step up from assuming that one is 0.7 and one is 0.5. Just assume one is bigger than the other one, and I think it would fall out. So this min-max fuzzy logic obeys the first form of De Morgan's law. It also obeys the second form of De Morgan's law. And as Sam pointed out here, I have the same A problem in the bottom. That A at the bottom should be a C. The A came from nowhere. I think that this could be proved similarly for assuming that B is greater than C. And if you just went through it and showed that everything worked out here, then I think that would probably work. Okay. I think going into ideas of rings and things would probably be killing a fly with a sledgehammer. Now, let me show you a place where fuzzy logic does not generalize to its crisp counterpoint. And this is something which is used in Western logic. What I'm going to show you is something I think very interesting. For a long while, there was literally a debate in circles, in more of the philosophical mathy circles, why fuzzy logic was best accepted in Eastern sort of communities as opposed to Western sort of communities. And the reason is because fuzzy logic does not obey the law of excluded middle. The law of excluded middle, which is used in a lot of proofs, for example, says that if you look at a set and you look at the complement of that set and you intersect them, you get nothing. right? All the points inside a circle intersected with all the points outside a circle, crisp set, and that is an empty set, right? And we use that to say, we use that in arguments to say that, there is a God or there isn't a God, for example, right? And we can begin to use that in ontological proofs of the existence of God, if you will. Well, it doesn't work for fuzzy logic. Now, why doesn't it work for fuzzy logic? It doesn't work because the min of a fuzzy set and 1 minus the fuzzy set is not 0. It isn't 0. Okay, let's see if I can get rid of this scribbling here. Let's take an example and see if we can reason why this is the case. Let's take the case of tall men, okay? Okay, let's look at 4 feet, 6 feet, 8 feet. Well, no, let's go back and do 5 feet. Let's go up a little bit lower. Okay, so these are different possibilities. Now, we would each give a different fuzzy linguistic value or different membership function for each of those. But I think all of us would come up with, as the height got larger, the membership function would get larger, right? So we might have something which goes like this, right? Well, I don't know. To me, 7 foot's pretty close to being in this set. Okay. So it might go up something like this. Is that fair? So that could be the set of men that are tall. So what would be the set of men that are not tall? It would be 1 minus this, right? And where does the intersection always intersect here? What is this point?
0.5.
That's always going to be 0.5, right? So 0.5 is the point of maximum ambiguity, if you will. It's the point of maximum ambiguity. It's not in the set. It's not out of the set. Heck, I don't know whether it belongs there or not. Now, if we look at the intersection of these two, and the intersection is the minimum, drawing the best I can, guys. This would be the intersection of tall and not tall. And it's not equal to the empty set. What is the membership function of the empty set, by the way?
Identically 0.
Identically 0. So if you have something which is identically 0, that's the membership function for the for the null set. Now notice, if we had, for example, guys that are over 6'5", or less than 6.5, and guys that were greater than 6.5, yeah, that's terrible. And that was one membership function, and another membership function, that their intersection, which would be the what? The minimum of both of them would be equal to 0, right? If we took the min of both of those crisp sets. So it would be the membership function of the null set. But up here, we don't have the membership function of the tall set. Should this bother us? I mean, we're so used to this idea of the law of, what was it? The law of, I get them
Excluded
mixed up.
middles.
Yeah, the law of excluded middles. We're so used to it that it should have bothered us. Well, think about this. A guy that's six, I don't know, say 6.5 foot tall. Okay. Is he tall? Kind of. Is he not tall? Kind of. So he's both in the sets of guys that are tall and not tall. And so therefore the intersection of the sets is not identically zero. It is not equal to the null set. So linguistically, at least to me, this makes sense. You're not in the set, you're not out of the set, you're a little bit in the set, you're a little bit in the complement of the set, and that's okay. And the maximum point of ambiguity is when you're half in the set and half out of the set. And that's where the intersection reaches the maximum, always is at the point 0.5. So for fuzzy logic, we do not have the law of excluded middles. That doesn't work. Doesn't work. Well, that doesn't do good. When you go back to your screen, you end up at the same place that you started the whole lecture with. So let me see if I can go back to here. Hopefully none of you okay, here it is. So it fails the law of excluded middle. Now, if we take the complement of both sides of A dot A intersect A complement, we get the law of contradiction. And here is the law of contradiction. It says that if we take all the points inside the set, union them with all the points outside the set, we get the universal set. What's the membership function for the universal set? 1. Yes, exactly. So the empty set is membership function is 0. For the other one, the membership function is equal to 1. So it doesn't work that way, just for exactly the same reason that that we talked about. The maximum mu sub A and 1 minus mu sub A is not equal to 1. So the law of contradiction and the law of excluded middle are not applicable for fuzzy logic. So it does fail the crisp boundary conditions, if you will, that we applied to everything else. However, I think we can explain it, at least I can justify it in my mind, talking about some of the fuzzy linguistic variables, that they can be in the set and in the complement of the set. And you know, that's okay. That makes sense. So we will talk about other fuzzy logics. There are so-called sum product logics, where instead of the minimum, we use the product of the two membership functions. And instead of the maximum, we add the two membership functions. Now, the problem is that when we add two membership functions, the summation cannot exceed 1. So we have to put a little cap on it. So if the membership functions add greater than 1, we just add 1. Now, originally this was used because there was so much in signal processing that was pre-wired to do multiplication and addition. And multiplication and addition are something which is very easy to use on processors. So this is some product inferencing, and we could go through the same challenge that we did for the min max and use some product inferencing and figure out what was going on. The complement, by the way, is exactly the same. It's 1 minus. We still use that. Okay, we can talk now about the Cartesian product, and this will be the last thing that we talk about here. And have you ever noticed when you multiply two vectors, you can either come up with what? You can come up with a single scalar, or you can come up with a matrix, right? One is the inner product, one is the outer product. If you multiply two vectors and you just get a single number, that's the inner product. If you multiply two vectors and you get a matrix, that's referred to as the outer product. So we can literally take the Cartesian product of some of these different membership functions, and this is an extreme example, and hopefully this extreme example will drive home exactly what we're doing here. Say, for example, we had the set of let's see, the set G of liquids that taste good and the set of cities close to Los Angeles. Okay, so let's look at the set or the membership function for liquids that taste good. I'm having 0.0 is swamp water, 0.5 is radish juice, and 0.9 is grape juice. The cities close to LA, we use the membership that we used last time, 0.5, 0.8, 0.9. By the way, this is not this is kind of the discrete equivalent of membership functions, right? We're assigning a membership function to each point as opposed to an entire function for the membership function. So this is referred to as a singleton notation. Does it make sense now to talk about liquids, the set of liquids that taste good and cities that are close to LA? Well, it's a little bit of stretch, but yeah, we can do that. We can talk about the set of liquids that taste good and cities that are close to LA. What does the and correspond to? It corresponds to the minimum argument. So we can, as you can see here on the bottom, take the membership function for LA cities and spread it in a row at the top. We can take the liquids, spread or concatenate them into the column shown on the left here, and then in each case take the minimum. And these minimum correspond to liquids that taste good and cities that are close to LA. And this turns out to be really important in control theory, as we'll see, because we do generate such outer products. Next time we meet, we'll talk about fuzzy inference. This is the basic architecture of the Mondami structure for fuzzy control that's used in a lot of commercial products. And we will find out the hoops that we have to jump through to do Mondami control. And we'll look at that. We'll look at that next time. So, are there any questions? Fuzzy logic's interesting, right? You know, what's interesting about fuzzy logic is that many times, when you're presented with something, all of a sudden it becomes a paradigm in your mind, and all of a sudden you see different instantiations of it. And I hope you do with fuzzy logic. I remember the first time I took a course in transmission lines. Man, I saw transmission lines everywhere. I even saw it in paper towels. I was always, well, toilet paper actually, but I question why does toilet paper, when you pull it, usually break at the roll instead of where you're handling it at? And then it occurred to me, well, I'm launching a wave along the toilet paper tissue. There's an impedance mismatch at the roll, and therefore there's a reflection, and that breaks the perforation at close to the roll. So everything began to make sense in terms of transmission lines. And I think that that's true with probability. I think that you're probably so entrenched in the area of probability that it's hard not to think about probability. But this new idea of fuzzy logic not being equal to probability is something which you'll see in a lot of different places as you just look around. The entire idea of the fuzzy linguistic variable, which we use extensively in what we do. And you'll notice this, hopefully, in your day-to-day discourse. Any questions at all?
I have a quick question related to the other fuzzy inference model you mentioned, the sum and product.
Yeah, the sum product, yes.
Is there like a direct correspondence between sort of that and models for just sort of standard Bayesian inference.
No, this has nothing to do with Bayesian inference. Bayesian is probabilistically, it's probabilistic. And this is, I've heard it said, I don't like the idea that probabilities are one thing and that fuzzy logic deals with possibilities. And I guess there's some truth there in that, and the probabilities and possibilities are different. But no, Bayesian is a probabilistic model and is a very successful model used to do things like sort our spam out, and is used in, to figure out whether an email message coming in should go in our spam folder or not. I mean,
Right.
that's one of the great applications, but there's no probability here at all. This is a totally different model. Fuzzy logic is a totally different model. It's a totally different model of uncertainty. It's the uncertainty ascribed to fuzzy linguistic variables. Now, are there cases where fuzzy and probability overlap conceptually? Yeah, they are. Hopefully, I've presented it in a case where they look pretty disjoint. And I wanted to present that where they were disjoint before we got into any cases where they were combined in any senses. But no, there is no Bayesian thing happening here at all. Okay, any other questions? Okay, if not, be well. I've put the links to this slides. I've also put a link to a paper. It's kind of a tutorial of fuzzy logic going through exactly what I went through in these slides. And and I also put a link to the slides which we used on the introduction to artificial intelligence. Those are also on the spreadsheet. So all of those are there. So go to the Google Sheets and you'll be able to access all of those. Okay, thank you all. Be of good cheer.